very much. I appreciate that. As was mentioned, I've been in the aerospace industry for essentially 23 years. The majority of that, 21 of those years, I've been developing launch vehicles, rockets. And so I'm going to talk about space, but primarily from the perspective of how do we get into space. I'll give a little bit of an example of some of these products that we put into space, some of the satellites, some of the spacecraft for exploration purposes, but primarily focusing on the launch vehicles and the history of launch. So a little bit of a history of space exploration going back to 3000 BC up to the present. Talk about the basics of rocketry. I think from what I've understood, you guys probably know how rockets work, so maybe I shouldn't go through that part of it. But nonetheless, I'll give you a little bit of that, talk about the Eld program, talk about some of the satellites that we put into orbit, talk about NASA's Constellation Program, and the types of space exploration that program should enable us in the future. Space is something that people have been interested in for 5,000 years or longer. The Babylonians used to look into the skies, chart out the stars. They actually defined the first zodiac back in 2000 BC. So space is something that has been of an interest to the population of the world since the beginning of time. Early on, it was already discovered that all the planets, the sun, rotated around, or all the planets rotated around the sun, and it wasn't until around 120, 130 AD that people actually started to believe that the Earth was truly the center of the universe. That perception was dispelled in the 1500s by Copernicus and Galileo Galilei when they started to develop new techniques to look into the heavens. The telescope was invented by Galileo, and with that new device, he was able to confirm that indeed the Earth was not the center of the universe, that the Earth rotated around the sun just like the other planets in the solar system. Kepler and Isaac Newton, also in the 1500s, 1600s, they developed the fundamental laws that told us how the planets rotated around each other, how they attracted each other, what their gravitational pull was. Those two gentlemen set the stage for all that we can do now as far as getting into space. Around the turn of the century, that would be the last century, not this one, 1900s to 2000, way before any of us was alive, there were three gentlemen around the world, one Russian, one German, and there was an American, that knew that we were limiting ourselves by not being able to get out into space to really explore the heavens and really understand what was going on. They were intent on developing rocketry so that we could actually get ourselves off this Earth and go out into the heavens. They looked at what the Chinese had developed back in 1300 BC, simple rocketry that was developed based on gunpowder. Gunpowder doesn't have the energy to get us into space. So these three gentlemen, Tsiolkovsky, Oberth, and Goddard, became the fathers of modern rocketry. They developed the technologies to get us into space. The first time that technology was really used was in World War II, 1944. It had no impact on the outcome of the war, but the Germans used that technology to launch missiles from Europe into London, trying to basically dissuade the British from fighting any longer. It did not work. What was so critical about that was the V-2 that was developed by Wernher von Braun became the foundation for all future space launch vehicles. The United States and Russians got involved in what was called the space race. During the 60s, it was an exciting time because we saw a lot of firsts in space access. The first satellite was launched by the Russians in 1957. First animal launched into space. The first human launched into space, all by the Russians. The Americans were slightly behind that, but we also launched our first satellite, the Explorer 1, in 1958. What was so important about that is that satellite actually discovered the Van Allen belt, which is a radiation belt that surrounds the Earth. 1961, first human in space, Yuri Gagarin, followed by Alan Shepard of the United States. John Glenn, first American to orbit the Earth. Neil Armstrong, Buzz Aldrin, first individuals to actually set foot on the moon. These were very heady times. This was a fantastic time for space. The last time we visited the moon was 1972, and then we started investigating space from the space station and from the shuttle. So how do we get into space? We use rockets. it's our standard right now. We need something that has high thrust, something that can offset the pull of gravity, pulling the rockets back on Earth. We also, as we speed through the atmosphere, we start to generate aerodynamic drag that's also trying to slow us down. So we need to balance out the thrust, the gravity, and the drag to get us into space. Thrust is provided by the propulsion systems on the rockets. We either use a liquid rocket engine, solid rocket motors, either one of those. They work on the same basic concept. We burn a fuel and an oxidizer in a high-pressure combustion chamber. We are then forcing that, I'm not sure if you can see this very well, but basically we burn the fuel and the oxidizer together, high pressure, forcing it out through a throat of a nozzle, through the supersonic section of a converging, diverging nozzle. That provides significant thrust that pushes the vehicle the opposite direction, basically using Newton's laws of motion. The only difference between the two is that a solid rocket motor, we have blended the oxidizer and the fuel together. We use a rubber binder to hold it all together, and then we burn that as a single mass within the combustion chamber. Liquid and rocket fuels are separated in a liquid rocket engine. We use what we're using now is generally liquid oxygen and either RP1, which is a kerosene-based fuel, or else we use liquid hydrogen, and I'll talk about both of those a little bit later on. We basically use pumps to pump those two liquids into a combustion chamber, burn it. Same net effect as having the solid rocket motors. What you have to realize with rockets is that the primary weight of a rocket is the propellants themselves. Over 90% of the weight of a rocket is propellants. The rest of it is the tank structures that holds the propellants. And then the rest of it is actually the payload. There's a rocket that we just launched. It weighs I'm going to say about 1.5 million pounds. Out of that rocket, 9,000 pounds was actually the satellite. So you can see that most of what we carry is actually propellant and structure. It's highly inefficient to burn all of that propellant and have all this structure still around it because you end up carrying dead weight. So we've developed over the past 50 years staged systems so that as you deplete your propellant in one stage, you basically jettison that stage, get rid of that dead weight that you don't need, and go to the next stage and burn the propellant in that and continue to go through each of those stages until you get to the final stage where you have an upper stage and the satellite. By the way, that's a DSP-23 satellite that was launched a year ago. That was my last launch that I was in charge of. So you end up with just that little piece of hardware at the top, and that is put out in space. We separate ourselves from that so it doesn't carry along our dead weight, and then it does its job for 10, 20, 30 years. We can't just put a rocket on the ground, light it off, and expect it to go where we want it to go. We need to have an autopilot, a guidance, navigation, and control system. There's not a man in the loop that is driving this car into space. Basically what we do is we preset a trajectory from the Earth to its final destination. We define when we're going to stage each component of the vehicle, and that's set in place prior to launch. The GNNC system basically identifies the actual position of the rocket at any time during its flight, compares that to where it's supposed to be, compares that to how fast it's supposed to be going, and it makes continuous corrections. I think it's at 50 cycles per second. So it's constantly re-navigating its position, redefining where it's supposed to go, and basically putting a rocket at exactly where it needs to be to drop the payload off where it desires. Where does it go? We've got multiple orbits that we put satellites in, each for different purposes. You probably have heard of a lot of these, but basically we put them in low Earth orbit, medium orbit, geosynchronous, or high Earth orbit. Basically, it all depends on what the mission of the satellite is. Weather satellites actually are in low Earth orbit, along with the shuttle or the Hubble telescope and the space station. Any of our Earth imaging satellites that go up there to understand the mineral deposits and other aspects of the Earth are put into low Earth orbit so they can get a very good image of the surface of the Earth. The GPS satellites, many of you actually have navigation systems in your cars. Each of those navigation systems is actually continuously talking to a series of satellites at 11,000 nautical miles. That's the medium Earth orbit. When you're talking on international telephone, you're actually probably going through a geosynchronous communication satellite, 22,000 miles in the sky. High Earth orbits are also used for communication satellites. However, they have special needs, especially if you're looking at the northernmost parts of the world or the southernmost, around the North and South poles, because geosynchronous orbits don't allow you to really cover that part of the globe. So we've developed a high Earth orbit. It's generally going to be highly inclined and a highly elliptical orbit. The inclination is basically the relative angle of the orbit relative to the equator. Zero inclination says that you're right at the equator, and there's a special case for the geosynchronous orbits that have a zero inclination. They're called geostationary orbits. Those orbits are such that the satellite is rotating around the Earth at the same relative rotational rate as the Earth is. So it effectively is sitting directly over the same spot on the globe for its entire lifetime. That's where we put our satellites for communication, so that we can constantly communicate any place on the globe by linking up to the same satellite. If you've got Dish Network or you've got another satellite TV system, you're basically communicating with one satellite that's constantly over your house. So that's the basics of rocket science: propulsion, targeting, and location. So what's the ELV program? It's the most recent development of launch vehicles since the 80s, I'm going to say, the 70s. It's actually a program where we developed two completely new families of launch vehicles, the Atlas V and the Delta IV. Lockheed Martin was actually the developer for the Atlas V. Boeing Corporation was a developer for Delta IV. They did this development for the U.S. Air Force. I don't work for, but I work with the Air Force on the development of these two rocket systems. The program started in 1995. It was a 7-year development program before we got to our first launch in 2002. It's destined to be the primary means of access to space for satellite and space systems through 2020. Why did we need a new rocket system? The cost to get into space was becoming more and more expensive. A Titan IV launch, which launched the heaviest and most expensive payloads that we put into space, cost $500 million per launch. Even our government couldn't afford $500 million per launch on a regular basis. So the whole purpose of the ELV program was to figure out how to get into space cheaper. The goal was to cut the cost of access to space by as much as 50%. So how do we do that? Prior to the ELV program, the U.S. had 4 primary launch systems: the Titan II, Atlas II, and Delta II, as well as the Titan IV. Each one of those rockets was developed with a singular purpose. Titan II launched nothing more than the DMSP, weather satellites, out of Vandenberg Air Force Base to put those weather satellites into low Earth orbit. Delta II was designed to put the GPS satellites into MEO. The Discus satellite was launched off of Atlas II. DSP-23 and all the DSP satellites, which are early warning satellites, as well as reconnaissance satellites, were all launched on the Titan IV. Very, very specific missions, very specific launch vehicles to handle those specific missions. Very inefficient use of our resources, though. Every one of those launch vehicles required its independent factory, independent manpower, independent launch facilities, independent infrastructure. So we were paying 4 times just to get into space. The idea of the ELV program was to say, how can we develop a launch system that can actually put in space any of those types of vehicles, from a small DMSP, which weighs several thousand pounds, to a DSP or a heavier satellite that might weigh 13,000 pounds, or even a satellite that might weigh 50,000 pounds and put into low Earth orbit. That was the whole reason we had the ELV program. We developed 2 families, the Atlas V and the Delta IV, because we learned some hard lessons in 1985. The Challenger blew up. I don't think you guys were around at that time. But the Challenger, the space shuttle, was the only way that we could get access to space at that time frame. When the Challenger blew up, we had no access to space. We didn't want to get back into that same condition in the future, so we developed 2 completely independent systems of launch vehicles so that we were always assured of access to space. The Atlas system is actually built using the technology gained over the past 30 years from the initial Atlas vehicle that was used to launch ICBMs as well as to launch man into space. Incrementally, it was evolved. What we had to do, though, what we wanted to do, was develop a modular concept for our launches. So the Atlas V basically took a very strong structure for a core vehicle that we could attach solid rocket motors onto if we wanted to, anywhere from 1 to 5 solid rocket motors. We could actually strap 3 of these core boosters together. And by mixing and matching components, using just one manufacturing facility, mixing and matching components, we could actually lift the full fleet of satellites that the U.S. had. Delta IV, we did the same thing. There was a little bit of a difference for Delta IV. For the Atlas V, they had already developed a brand new rocket engine for that system. Delta IV, we still were relying upon 9 solid rocket motors and a small little RS-27 liquid rocket engine. That's a very inefficient use of taxpayer dollars. We wanted to develop a brand new engine that could replace the capability of all 10 of those systems. That was the RS-68, first new development program of a liquid rocket engine of that size since the Space Shuttle main engines back in the 70s. It took a whole new structure and, again, a modular concept, mix and match the number of solids, mix and match the number of boosters that you want to put on that thing, and it's basically dial-a-rocket type configuration. The RS-68, again, it's the workhorse of the Delta IV program. Rocketdyne had developed a whole fleet of engines, from the J2 engine that was used on the Saturn V program. Every one of the LOX-RP engines that was used on the Atlas II or the Delta II programs were built by Rocketdyne. They built the Space Shuttle main engine. They also developed a cheaper version of the SSME, which was more for development purposes to show that you could get a more cost-effective version of that engine. We worked with Rocketdyne to develop a new capability that was driven by simplicity and robustness as opposed to high performance. Again, simpler design. We wanted to reduce the number of parts. We wanted to reduce the amount of time it took to manufacture this engine. Ultimately, drive to a lower cost. That gave us the RS-68, and that's what we're flying today. One of the things that we found is that satellites continually get heavier. They don't believe in getting lighter. They want more capability. So we're going through some trades right now, looking at the simplicity of the design, seeing if we can maybe regain some performance for this engine by beefing up the turbo machinery, the turbine, the pumps, and so forth that feed propellant into the combustion chamber. Beef that up, get slightly more performance, maybe 5-7% is all it's going to take. And that'll define the RS-68A, which will fly in 2010. NASA's going to take this capability, and they're going to use it for their next generation launch system. They're going to make some modifications for operability, and they're going to call it the RS-68B. We constantly look at our technology, constantly try to improve it incrementally to get more capability, but at the same time try to keep the cost down. Some fun facts about the RS-68. We use liquid oxygen, liquid hydrogen. Liquid hydrogen is stored at 400 degrees below zero. We mix it with liquid oxygen in the combustion chamber. We light it. It reaches a temperature of 6,000 degrees Fahrenheit. That's enough not just to melt iron, it will vaporize iron. That's how much energy we release when we combine LOX and hydrogen. When we light off an RS-68, it gives us the equivalent energy release of the Hoover Dam, 11 Hoover Dams for one RS-68 engine. That's pure power. 17 million horsepower is equivalent to 50,000 Maseratis. It's powerful. That's why I'm in the business. I love the power of rocket engines. We strapped 3 of these together to create a heavy launch vehicle. At liftoff, the 3 engines combined put out 1.6 million pounds of thrust. The rocket itself weighs about 1.4 million pounds. So we don't have a whole lot of excess thrust capability for this system, but that's a boatload of energy coming out. After 2 minutes of flight, we've consumed half of the propellant on that thing. We burn 1 ton, 2,000 pounds of liquid oxygen, liquid hydrogen per second with each of those engines. If you have a Porsche, we can throw 2 of those out a second out of each of those engines at 9,000 miles per hour. Talk about some power. We can put 50,000 pounds of a satellite into low Earth orbit. That's like taking a school bus, fully loaded with kids, put it into LEO orbit. So what makes the ELB program so special? Simplicity is the bottom line. We wanted to reduce the number of parts and the number of hours it takes to build these rockets. The R-68 only requires 20% of the parts that are used in the SSME. Again, reduction in part count. It takes less than 10% of the time to build an RS-68 than it takes for an SSME. The SSME, again, is the engine used on the space shuttle. And we've cut the cost by 80% for the production of that engine. As I mentioned earlier, we took one engine, the RS-68, and used it to replace 9 solid rocket motors and a liquid rocket engine. Simplicity in design. What else makes it special? We've gotten rid of all 4 of those launch pads for the Titan II, Delta II, and Atlas II. We now have one launch pad that can launch the full fleet of Atlas V launch vehicles. We have another launch pad that can launch the full fleet of Delta IV launch vehicles, every configuration to put any satellite that we have made into orbit. We used to spend a lot of time processing our vehicles at the launch site. We would spend as many as 30 days or even 4 months on the launch pad itself for Titan IV. We would use 18 different facilities for the Atlas II. We would use, I think, 30 facilities for the Titan IV. We now only use 3 facilities out at Cape Canaveral for the Atlas V. We spend 1 day on the pad. That's the day of launch. So what's so special about it? Very robust design. More efficient manufacturing processes. More efficient launch operations. More flexible payload capability. Dial a rocket. Bottom line is it's lower cost, inherently higher reliability. How reliable? These are the 12 launches that I was involved with. That's only half of the launches that we've launched on the ELB program. We've launched 22 rockets since 2002. Every one of those rockets has been a successful launch. The probability of doing that, you wouldn't believe it. Historically, out of the first 3 launches of a brand new launch vehicle, you can expect one of those 3 will be a failure. We beat the odds on this program. We have 100% successful launches. Statistically, that says you have a 94% demonstrated reliability compared to the very mature programs of the Titan IV, Delta II, Atlas II. They were able to prove over their lifetimes a 97% reliability. Brand new program has already demonstrated reliability on par with very mature systems. The commercial market for launches is only about 90% reliable. We've already exceeded the reliability of those other launch programs. This is a short video. It's about 5 minutes long. It's going to show you some of the manufacturing capabilities for the Delta IV. It's also going to give you a short clip of a launch of the DSP-23 satellite. Assuming it comes up. Maybe we won't see it. It was a good video. And I showed it before this presentation. Okay, let's try something. This rocket, each of those boosters is 5 meters in diameter. That's 15 feet. The total stack is 300 feet tall. This is a gentleman doing final processing of the upper stage, and what you just saw was the booster for this rocket. Those guys were looking inside the engine bell for the R-68 engine. We used robotic machining capabilities and techniques to basically create out of sheet aluminum, several inches thick, the structure of the tanks. We also use a lot of composite materials. So a lot of robotic operations for the construction of this vehicle. Minimize the amount of time and touch labor that we had on the rocket. In a second, you're going to see them roll this brand new rocket out of the factory, and we'll ship it to Cape Canaveral. rocket this big being driven out of a building, and you're walking next to it, it just kind of stops your heart for a little bit. You wouldn't believe the excitement. We transported it by barge from Decatur, Alabama to the launch site. That was a Delta Mariner. We can actually put 3 boosters in there, an upper stage, payload fairing, so we can have a full stack. We take it to the horizontal integration facility, mate the different pieces together, and then we drive it out to the launch pad. This thing, the K-Mag, can go a whopping 10 miles an hour unloaded down the road. When we have a vehicle on it, you can see these guys are walking next to it. That's how slow it crawls. We'll take it out to the launch pad. It goes on to what's called a fixed pad erector, which basically transitions it from the horizontal to the vertical position on the launch pad. It's going to go pretty quick, but in reality it takes several hours to actually elevate it into that position. It's not quite that quick. We finish processing the vehicle on the pad. We put the payload on top of it so that we're fully mated. We do final checkouts. On day of launch, we roll back the tower. We load it with LOX and hydrogen. Again, it doesn't quite move this fast. And this is when it gets exciting. We had some onboard video you'll see later on, those strap-on motors falling away from the vehicle.
5, 4, we have ignition of the main engine. 2, 1.
That is a ball of hydrogen flame
of a United
going up
Launch
the vehicle.
Alliance Delta IV Heavy rocket carrying DSP-23, the final DSP missile warning satellite for the United States Air Force.
From the Mission Director Center, which is where I sit, about a mile and a half, 2 miles away, you sit there, you watch this thing slowly lift off the pad. You're wondering if it's going to make it. All of a sudden, it gets high enough up that you're basically underneath it. The entire building is shaking. The pounding of all that thrust, 1.6 million pounds, is just overwhelming. The 2 strap-ons are about to burn out, and they fall away from the vehicle. There they are. That's one of the 2 falling back to Earth. This is inside the payload fairing. We're going to get rid of that excess weight. It's jettisoned because we're outside the atmosphere. We don't need to protect the satellite anymore. We deploy the nozzle on the second stage engine. This is an RL-10 built by Pratt & Whitney Rocketdyne. Deploy the nozzle, light the engine. That nozzle is 2,000 degrees Fahrenheit. Carbon-carbon, very hot, able to withstand those temperatures quite easily. This is a DSP-23 satellite separating from the booster after a 7-hour mission. You're going to see the solar panels deploy in a second. They lock into place. They wiggle and wave goodbye. When you're in the launch business and you realize that if you make a mistake, you throw away $1 billion worth of satellite, that is an exciting sight to see it successfully put in orbit. So what do we put in space? Communication satellites, navigation, weather satellites, early warning satellites, defensive satellites, reconnaissance, earth science, and space exploration. If there's any reason to go into space, we'll put it into space for you. Comm satellites, the first 2 satellites we put in orbit for the Delta IV program and the Atlas V program were built by Eutelsat. These are commercial communication satellites. They transmit TV, radio, broadband internet. They have satellites throughout the world that are basically there to help you have good commercial communications. For the military, we have the Defense Satellite Communication System. It's been the workhorse of military communications for the past 20 years. It has high data rate, secure communication for the Air Force, the Army, the Navy, all military services, including White House communications. We launched the last two of those in 2003, Discus A3 and B6. The follow-on system is a wideband global system. This will provide an order of magnitude greater communications ability than the Discus systems. There are 6 Discus satellites in use right now. A single wideband system can replace the data rate of all 5 or 6 of those satellites. What we're seeing with the evolution of satellites, we're looking for bigger, better, more powerful, more capability, which means bigger rockets. Global positioning system, I mentioned this earlier. These things sit at 11,000 nautical miles. There's 24 of them in space. Your GPS detector that you've got in your car, maybe you have a handheld device. It basically is talking with 4 of these satellites. It's actually talking with more of them. It selects the 4 best satellites that have the best signal, and it basically uses fundamental geometry. Each satellite broadcasts the time of day using an atomic clock that's all synchronized. It broadcasts its position in space. Your GPS system basically picks that up, triangulates off those 4 satellites, figures out the exact location you're at, plus the exact time of day at your location. Weather satellites. There's 2 different types of satellites. One's a geostationary orbit. When you watch the news, 7 o'clock news, you look at the weather channel. They're actually broadcasting from the GOES satellites, the geostationary orbiting satellites. Those things basically observe, track, monitor weather formations, whether it's thunderstorms, whether it's a hurricane off the coast of Florida. They track it and they use that to project where it's going to go. To really be able to forecast the weather patterns, we use a DMSP satellite, Defense Meteorological Satellite Program. It sits at 400 nautical miles. It flies over the North and South poles. It covers the world in basically 12 hours. It measures the temperature and moisture content of the air all the way through the atmosphere. It can tell you how high the waves are in the ocean. It can tell you what the temperature of the surface of the Earth is. It can tell you how much snow is on the Earth. We use that type of information to help generate weather forecasts for the next couple days, next couple of weeks. It's used extensively for mission planning for the military. Early warning systems. During the height of the Cold War, we were deathly afraid of the Russians and the Chinese sending ICBMs into the United States. Developed this capability called the Defense Support Program. That launch that you just saw was the last of the DSP satellites. There's 23 of them. They basically monitor, they have an IR sensor that's looking down on the Earth. It measures or monitors the plumes coming off of rockets. It tracks the trajectory of those rockets, and we verify whether they're coming to the United States or off into some other location. Gives us an opportunity to take defensive measures. SBIRS will be the follow-on system. Not only will it be able to detect ICBMs, but one of the deficiencies of the DSP system is that it's a global type observation. The SBIRS system will actually give us tactical awareness of short-range ballistic missiles or short-range missiles so that our warfighters in Afghanistan or in Iraq will be able to see a missile coming at them quickly, be able to take very quick responsive action, even if that flight time is minutes instead of hours. So that's the military use of space. NASA also uses space. You might have figured that out. But anyways, NASA does all the space exploration, they do the manned research in space. President Bush 3 years ago said, we haven't been to the moon. We haven't really done exploration for a long time. He told NASA that you will put a man on the moon by 2020. You will enhance our ability for scientific research in space. You'll create the stepping stone to allow us to get to Mars. So how is NASA going to do that? They're developing the Constellation Program, which is the next generation of launch systems for NASA. It basically consists of a manned Orion spacecraft, which is a larger variant of the Apollo spacecraft that we've launched in the 60s. A lunar lander that's, again, a modern, larger version of what we launched in the 60s. The Ares 1 and Ares 5 launch vehicles. The Ares 1 basically will replace the shuttle. It will take men and women back to the space station. We're going to basically use, again, the same way we did with the ELV, well-based technical or technology, flight-proven technologies, the J2 engine off the Saturn V, the strap-on solids off the Space Shuttle, the RS-68s off the Delta IV. I believe they're planning on using the electronics from the Atlas V. Take those, tweak them, modify them slightly, but maintain that basic technology, create these two launch systems. For trips to the moon, we'll launch the Ares 5 and the Ares 1. The manned capsule will be basically mated with the Earth departure stage on the Ares 5, and that will take it to the moon. From a scientific perspective, what's really great about the Ares 5 is that it provides, I believe, somewhere around 7 times the capability of a Delta IV. That opens up new avenues for interplanetary studies, space research. What are we going to do with that amount of lift capability? The Hubble Space Telescope is a 2.5-meter mirror. We can launch a 16-meter mirror in that type of system, 8 times, or actually about 6 times the size of the Hubble. That will enable us to look farther into the universe, farther into the history of the universe, help us to understand how the universe was formed, how the galaxies were formed, and how the planets were formed, and how they've changed over time. We're also looking at heliophysics, which is the study of the solar system, specifically the sun, and its effect on the rest of the solar system. One of the options that's being considered is to take some probes to the very close locations around the sun to monitor its weather patterns, if you will, to understand solar flares, to understand the magnetic attraction and magnetic fields at the sun, and understand how they affect the Earth's weather, how they affect satellites, because solar flares actually affect the way electronics work. We need to understand that better. Also, follow-on missions to the edge of the solar system to understand what's in that boundary between the solar system and the galaxy, the heliosphere. Some great research was done. The Voyager satellites or space probes were launched in 1977. They're still living, they're still flying, they're still sending back data. We want to get more information about what's out there at the edge of the solar system. Some of the other options are to go to other planets, such as manned missions to Mars. Perhaps go to the outer planets of the solar system, things that would normally take 30 to 50 years to get out there. This will help us get out there much quicker, have more technology on those space probes, help us to better understand the genesis of those planets, and understand perhaps the genesis of life or potential for life on some of those other planets. Some of the other things that NASA has been doing to enable space exploration. I mentioned earlier how much propellant that we carry on a launch vehicle. That doesn't leave a whole lot of room for scientific experiments. So what NASA's doing is looking at alternate propulsion technologies. The solar sails, basically the same concept as sailing across a lake, only we're using solar energy to drive ourselves across the universe. Electric propulsion uses a very small amount of propellant, uses the electric energy to heat it up, to excite it. It's not even heated up, it's just excited to extremely high velocities, high performance, maximize the benefits of that propulsion system to take our vehicles out into the far reaches of the solar system. Aero capture, once you get out to a planet like Mars or Neptune, you're going at 17,000 miles a second. You've got to slow down. Aero capture helps you do that. This is a aero shield, which is very much like what we used on the Apollo program. You fly into the atmosphere. You use the atmospheric drag to slow you up. You dissipate the heat with a shield. The other option is to take advantage of the atmospheres at the higher altitudes. You need a lot larger surface area to do that. So these are deployable systems called balloons. It's a combination of a balloon and a parachute. You deploy these, big, large surface area, helps you slow down much quicker. You don't get nearly as hot, and you save a lot of weight than for your scientific experiments. So that's where we've been, what some of the opportunities are in the future. It's all built on technology. We have a need to improve our launch capabilities because we need to get those satellites into space to better utilize space. We need to put those space probes into orbit so we can better understand the genesis of the universe. We need new sensor technology. we need continuous development of new capabilities and new technologies. And that's what I've got for you. Any questions?
Well, thank you very much for a very fascinating talk. So now we have time for questions.
I'm sorry, I can't hear you. My ears are going bad.
How come you guys haven't tried to go to the moon since '72, and you're now trying to go to the moon when the president asked you to?
Not my decision. No, that was a lot of it was really based on political motivations. During the 60s, we were in a very tight, it was a Cold War period. We were in a battle, a psychological battle with Russia. We wanted to be the first people to the moon. We went out there, we found what the moon was made of, we understood the moon, and the excitement was over. So for political reasons, they canceled the space program. We'd been there. What more can we do? What President Bush wants to do is to use that as a staging location. Let's go out there, develop colonies, so that we can then, we now have the technology, let's use that as a base to lift off and go to Mars and other planets. So now it's not as a endpoint, but as a stepping stone to other research.
I've heard of another launch system that they've been developing. It uses magnets to actually accelerate an object enough to actually send it into a lower space orbit. Is that true?
There are magnetically driven propulsion systems. They've been in development, I'm going to say, for 20 years. They were initially developed for kinetic energy type systems. To say that whether they can put a satellite or a system into orbit, I really can't say. I haven't been involved in that. But I know that they do take magnetic fields, and you have basically very little friction in those types of devices, and you can accelerate structures to extremely high velocities. Whether we can put something into space with them or not, I can't say. I'm sorry.
Why did you guys choose to develop two different systems, like the Delta and the Atlas?
It was basically, initially we were going to only develop one. We felt that we could develop and build these systems with sufficient reliability that we would only need one family of launch systems. There was a problem with that philosophy. In 1998, we lost two Delta IIIs, a Delta II, Titan IV, and an Atlas. Our entire capability to put satellites into orbit was thrown out the window within a 6-month period of time. We realized that flying to space is not an easy endeavor. It's a dangerous endeavor. We wanted to make sure that in the event that we had such a catastrophe in the future, let's just say that the Delta IV had some major problems with it, we couldn't get it off the pad, we needed to have an alternate way of getting into space. So we wanted to keep the two of these systems going simultaneously so that we can ensure that we have an ability to put satellites into space. That question that you just asked is constantly on the tongues of congressional members, congressional committees, people that are watching the budget. Why do we have two vehicles out there? It's always going to be a good question, and it's always a matter of how much risk do you want to accept. Do you want to put all your eggs in one basket or keep two families so you can make sure that you do have an access to space?
Somebody over here had a question.
If an ICBM is launched, how much time do we have?
About 45 minutes. Not a whole lot. It takes about 90 minutes to orbit the Earth. So if you're going half the way around the Earth, about 45 minutes. So it's duck and cover. And that's why the SBIRS is so important, because if you're looking at a theater-type defense, you need something that's even more reactive within a matter of minutes, not 45 minutes. Question down here?
Is it true that we have solar panel satellites that are capable of sending energy absorbed from the sun back to Earth?
There is, the question is it true that we have satellites that are capable of capturing or harnessing the solar energy and sending it back to the Earth? To my knowledge, that capability does not exist today, but there are people that are looking at it and investigating capabilities to do so. You can actually put a mirror into space, you can harness the sun, and then focus that down to a collector on Earth. So that capability does exist. It's a matter of return on investment as to whether or not we would really do it. But there are people that are looking at that capability. You guys are challenging me.
How much do the astro, or should I say xenobiologists, bug you to go back into space?
How much do they bug us to go back into space? Every element of the space sciences community is thirsting to get into space. They want to know more about the planetary structures. They want to know more about life on other planets. They want to know about the origin of the universe. Every facet of the space community is thirsting to get back into space and to do more research in space. So I'm not sure if that answers your question, but people are generally inquisitive and they want to learn more, and they're always asking for more opportunities to get back out into space.
There's a question down here.
When the rocket is going up and the two side rockets fall, where do they fall to?
They actually fall into the ocean. They're about maybe 100 miles off the coast of Florida when they fall. They land in the ocean and basically sink. And now you're going to ask, why am I putting litter in the ocean? Basically what happens once they fall in the ocean, we make sure that there's nothing out there. We have a clear zone to make sure there's no boats, no people, so nobody's going to get injured when we drop these things into the ocean. They do crumble when they hit. They sink to the bottom of the ocean, and sea life actually starts to grow on them. You start making basically an artificial reef, and you're actually helping to spawn additional life. We've got a whole bunch of what would be called trash in the ocean off the coast of Florida, and that has actually generated new habitats for fish down there.
Thank you. How much do the chemicals used to propel the rocket harm the environment?
That's a good question. The system that I showed you on that video is it's a LOX hydrogen system. It burns, and the products are water and water. So it basically does not do any harm to the environment with that particular system. Some of the older systems that we had, we used solid rocket motors. They actually generate a lot of hydrochloric acid, HCl. That would actually cause damage to the ozone layer, and it would cause damage to the area around the launch pad. So we've tried to minimize the use of solid rocket motors. We still do use them to a certain degree, but not to the magnitude that we used to. And again, those drop off within about 100 seconds after launch. They do not actually penetrate the ozone layer, so they don't do the same type of damage that we used to do with the older rockets. What's the process that a rocket goes through when it returns to the Earth? For these particular rockets that I showed you, they're expendable launch vehicles. So the two core vehicles, actually 3 core boosters, all fall back into the ocean, and they just tumble. The upper stage generally goes into an orbit that will slowly decay over time, and it will re-enter the atmosphere and generally burn up, although some of it does distribute itself around the world, mostly into the ocean, but sometimes on land. Those are just free-falling bodies. For a vehicle like the Space Shuttle or the Orion system, what they will do is basically using their maneuvering engines or motors on the capsule, they'll reorient themselves to make sure that the heat shield is properly positioned. They'll target a certain spot on the Earth, and then knowing basically what the atmospheric conditions are, the pressure, the density, and that type of thing throughout the atmosphere. You'll target it and basically just ride through the atmosphere and get extremely hot. So it's a targeting exercise is what it is.
Okay, one last question.
Is there any other types of fuels that are more cost efficient?
Not what the more cost-efficient fuels that we can use. Actually, the most cost-efficient is probably RP1, which is kerosene, which is a petroleum-based propellant. We've used that for a very long time. It's very cost-effective. Gone up in price recently because of the oil crisis, but other than that, it's a very cost-effective propulsion fuel. Liquid oxygen is relatively inexpensive. Liquid hydrogen is relatively expensive. It takes a lot to make hydrogen. Are there cheaper ones? Not really. Not as efficient. And it's always a trade-off between the performance and the power you can get out of the propellants and the cost to make them. And this is the best cost-benefit ratio that we've got.
Okay, let's thank Dr. Brosmer again.
Thank you very much. Appreciate it.